I was actually very intrigued looking at the embed developments that you talked about. The other day we were having chats with the teaching committee in the university. They were basically saying that we have embed in first year, in second year, and also in third year, and it's pretty much getting on the way everywhere, so we need to do something about it. But after looking at your contents, I think it's about time we look at it differently as well, not just discard this stuff. So my name is Rishad Shafik. I'm from Newcastle University, and Alex Yakovlev is here. Together we had been launching a campaign called Real Power Computing. We talked about this last year as well. It may sound very similar to something like real-time computing to you, and that's why it can be a bit confusing as well. But I will go through the concepts initially, and then we will show some of the hardware developments and also some of the other developments that we have in this particular domain. So, very generic kind of overview of the energy challenge that we have right now. If you conceptually divide the application domains in different power bandwidths, meaning that the kind of power bands that they actually belong to, you can pretty much have the high-end computing on the right-hand side and very low-end computing on the left-hand side, and you have all these different kinds of computing in between, like, for example, desktop computing, microservers, portable computing, personal mobile computing, embedded systems, and of course the ubiquitous systems. Now, let's look carefully and also closely. As you look into the right-hand side of things, because the workload is different and also the machines will have to sustain the workload. So these computers are built differently. They're not necessarily built with the same kind of energy efficiency that you would have on the left-hand side. When I say energy efficiency, I'm looking at something like the number of hours you could possibly operate with a given amount of joule. So it's a bit like you have only one lemon, but how many lemonades can you make out of this? You probably would make more of this on the left-hand side. Now, that's interesting because we need more and more energy efficiency because we have batteries, we have energy scavengers, and all these portable energy supplies that we have with us right now. But what's also happening at the same time is that the reliability of the energy supply is also decreasing as you go from the right-hand side to the left-hand side, meaning that there will be variations in the energy. Some of the variations you're looking at the ubiquitous systems will be in the range of, let's say, 2 orders of magnitude or even more. So that's very challenging, especially from the electronics point of view, because you have to design the electronics to survive, sustain, and also compute under unreliable power supplies. Right, and that's where we bring in the concept of real power computing. I'll introduce the fine line of comments a little bit later, but the highlight here is that as you have the energy supply is becoming more unreliable, you're also asking for something which is conflicting, which is you're asking for more efficiency out of this. You're actually asking for more operational time per joule of energy. Now, as you can see, we are obviously this is something that ARM has launched a campaign on. I had the privilege of listening to Rob's talk about trillions and the challenges that you have from the ARM's point of view. There is going to be, unfortunately, more electronics than we can imagine in our lifetimes. Trillions of them. So that would mean that you'll have to produce the underlying IPs, electronics, ecosystem of support, and everything else around it. And that will mean also that you'll have to scale your productivity needs from what we have right now to a whole new level, possibly to a factor of, let's say, 100 times faster, maybe. And that's something that we have to do not for the sake of, let's say, doing high-level synthesis or design automation or anything of that sort, but also with the fact that we don't have the manpower to maintain so many different kinds of electronics. So we have to live with the limited amount of manpower and engineers that we have. Now, what makes it even more challenging is the fact that the trillions of electronics, they are not of the same kind of domain of applications. They have different domains, different requirements. We talked about security. We talked about reliability in one of the other workshops or presentations. And there is also going to be a new, always new kinds of challenges, new kinds of requirements coming up with different kinds of diversity. My most favorite one, and also something that I'll be delving on today, is the energy autonomy. How can we make sure that the systems are automatically intelligent enough to formulate the energy that it would be using and it will be living with over time without having to be told or maintained over time. Energy, autonomy, and intelligence is the one that I'll be talking about, and that's where I think the real power computing fits in very well. Again, very high-level descriptions of these things, and then I'll steer you to the more engineering application of what we have here. So the basic idea is that electronics will basically formulate the energy or power budget, if you like. Power budget meaning if you have a certain power, and if you know how long you're going to run for, so what you basically have is some kind of energy budget as well. So you start formulating the power caps, also the power limitations that you have, and then you also predict how long you'll be running that application for. Then you can initiate the computation tasks or even the sensing tasks, processing tasks, transmission tasks, all kinds of tasks based around it. Meaning that you will not be retaining, you will not be you will not be in a position where you have not finished the computation but the power has gone out. This is called awareness, self-awareness in many ways. Yeah? Intelligence or autonomy, very many terms that we have. So how do we, for example, if you have a system where there is no option for energy storage at all, it could happen in energy scavengers, for example. You don't have any energy storage option at all. So you have to live with these kind of transparency from the high-level side. That would mean that you have to do a lot of offline characterization, understanding how the energy supply works, and also understanding the variations over time, and making sure that the developers and also the ecosystem of the systems that you ecosystems of devices that you have, they always know how to deliver on the computation based on the power budget. Okay. So two things to remember here. This is something we'll be referring to, something that runs without any energy storage, and also extensive power compute co-design. We'll be terming it as hard real power computing, something similar to hard real-time computing you might have heard. If I take the analogy again, hard real-time computing basically means that you have a deadline and you have to make sure that you provide your compute within the deadline. Likewise here, because you do not have any storage, you have to live with whatever power you're going to generate over a certain period of time. Right. Now, of course, if you have the hard one, you also have the other one, which is the soft one. Soft one will have the leverage of having a bit of energy storage, and that will make things a slightly easier for you in many ways. You can sometimes formulate the power budget, but you can overdo things in terms of, for example, consuming a bit more power, or sometimes you underdo things consuming a little less power. But what you eventually make sure is that you have the average energy usage that you have is something that you predicted or that you originally formulated for. These kinds of systems will have a bit of storage, and that will give you options of doing both design time and also run time adaptation at the same time. That's great. So what we're talking about is systems who are energy intelligent in many ways. But the intelligence requires, hardware, software co-design, providing awareness, and also design sort of an adaptation that provides robustness for the power variations that we're looking at. So the kind of power variations I've shown over here is typically in the low end, but imagine if you have the power variation really, really large, you'll need to design the electronics for it as well. Can I design electronics that is elastically grow or shrink based on the power supply, scavenged power that is coming in instantaneously? Now, there have been, I think, in very many grounds, there have been some piecemeal works from the community with different names: transient computing, power adaptive computing, energy aware computing, on-off computing, all kinds of things. And we have been designing very many silos of solutions and those things. But I think the three major challenges for real power computing are these. Number one, at the moment, the way we grow and shrink the computation is basically based on some system level or hardware options. For example, changing the frequency, changing the voltage, or even doing something smart with the sub-silicon smartness in terms of clock gating and all those things. But that only gives you a limited number of options, because the heterogeneity in terms of the operating points that you can have is only limited to certain points, right? But what we want, because the bandwidth of the incoming power is so large, we also want the computing options to be also stretched over a large dynamic range. What we are basically saying is that, can we stretch this one to a larger range? I would actually like to cite here that, for example, ARM's big little is a great example of stretching that beyond the individual course. But what we're talking about here is basically not just ARM big little, but very big, big, little, tiny, super tiny, and so on. Something that has options of computing at various ends of the power domain. Right. And there's another beast which is often forgiven and also forgotten, robustness. Because we want to design our electronics to survive that level of variation in the incoming power, sometimes what we do is we start designing a very complicated clock tree, power supply, delivery mechanism, and everything else. But what would be really nice is that we have a very simple power supply, but it's something that can work with a large domain of power variations. So it can still compute not only within the lower range of power supply variation, but also over a large domain of power variations. Now, this is something I'll be highlighting today in the example that I'll be picking on. And of course, there is also a continuing challenge, which is the survivability at zero cost. Today, the survivability or retention is basically initiated by something called, let's say, dynamic retention or retention problems. So if you look at the typical examples of retention, you're looking at 3 milliseconds, roughly 3 milliseconds of sleep time, before you go to sleep. And then again, another 3 milliseconds to basically wake up again. So you're losing 6 milliseconds of compute time because you do not have the zero cost survivability. So can we design electronics that will have automatic retention like biological organisms? For example, when we're low energy, we automatically know how to go to low energy mode and survive. Now, this is something which is a bit like instinct that the hardware does automatically for you, or the runtime and hardware together does it automatically for you at zero cost. You don't have to do anything else. The application developers will not have to worry about it. This is something the system automatically provides you. Right. So as I said and promised, that I'll be showing an example of something that we're working in this particular domain. That can we design electronics that will be working without any problems across a large range of power domain variations, so power variations. And this variation can come in the form of frequency, or it can come in the form of voltage, but we want to make sure that the computing survives no matter what. Now, I picked up this example of something that we have been recently working on. It's largely a work in progress, but there's a lot of potential, I believe. Something called Perceptron design. And if you're not from the machine learning community, Perceptron is something new to you, but just a little primer to this one. Perceptron is basically something that looks like a Mac, multiply accumulate circuits. So you have a good number of inputs, and you also have the corresponding weights. And the inputs and weights, they're actually pairs. They're multiplied like a dot product, and summed up together in the accumulator. And finally, you compare against, with some bias being added, you compare against some reference. And what you do is if the sum, accumulated sum, together with the bias is above a certain value, you say this is the class. And if it is below the certain value, you call this is another class. A typical very high-level example could be simply taking some feature data from little pet animals, and then finding out that, which one is a dog and which one is a cat. As you can see, the cats are always here, which is great. So this is a very simplistic example, but why it is important, the perceptron is an important element, is because this is the basic building block of many machine learning applications. Some of the modern neural networks, they have basically hundreds of thousands of perceptrons built in the system. So as you can see, one of the things I want to highlight here is that you have multipliers. Can you see? Multipliers are one of the most expensive components in the digital circuits. And you also have accumulators. It is not. It is less expensive in many ways, but it's not something to be forgotten. Okay. Now, what we did is we thought very hard and about it, and then we came up with a thinking that, look, we don't necessarily need to compute in the spatial domain, where we have, let's say, 1011, meaning there is a certain data. Can we transfer from the spatial domain to something called temporal domain? For example, duty cycle. Okay, so why am I showing inverter here? Inverter is something that can work with duty cycles, and it can produce duty cycles at the output. For example, anything that you put here, high input here will be low over here, and low over here will be high over here. So now if you do a periodic rectangular pulse at the input, you'll also have a periodic rectangular pulse at the output. The only relationship is that the output of this one will be proportional to the VDD, and also proportional to the duty cycle, and completely agnostic of what you have put in at the input side. Yeah, in many ways. So this is a fantastic property, which basically means that if you change the VDD, yeah, if you change the VDD and also the frequency that you have at the input, the output is still going to be defined by a duty cycle. And that's really good, because that's something that will give you the stretchability across different power domains, because voltage and frequency are the ones that, pretty much that define the power in the circuits. So then what we did is, unfortunately, the legibility is very poor, which is very unfortunate. I don't know why. Okay. So what we did is we tried with different configurations of this inverter, with or without registers. As you can see, with register, without register, we have a bit of skew in the duty cycle. As you increase the duty cycle, obviously this is an inversely proportional relationship, so output will be decreasing almost inversely proportionally and linearly. That is the expectation as you increase the V, as you have higher V out. Okay, so the duty cycle will define your V out, and the V out will be decreasing as you increase the duty cycle. As you can see, there's a bit of skew. That is mostly because of the disparity between PMOS and NMOS that you have, and you can probably mitigate that skew, by incorporating a bit of register over here. But that's something we can possibly ignore in many ways, because registers are not something that you'd like to fabricate most of the time, so it's not really a fabrication-friendly component. Now, we also went on doing some analysis and experiments to basically find out how robust it is against frequency variation and also the supply voltage variation. Again, I'm really sorry, the legibility was, it was supposed to be all right, but I think the resolution or something like that picked up on. So, okay. So input frequency, we varied the input frequency all the way from literally less than 1 kilohertz to 1500 megahertz, a very dynamic range. And we still saw that the output barely changes, only slightly increases at the higher frequencies, because you have the parasitic capacitances offering less impedance at higher frequencies. And the other fantastic thing is that as you keep on varying the supply voltage from, let's say, very low voltage, which is 0.5, all the way to 5 volts, even then, apart from these near threshold points, most of the time you have pretty much like a straight line, which is fantastic. So if you now take the combination of the supply voltage variations and also these frequency variations, can you see the dynamic stretch of power that you could possibly have in going into the perceptron, and the perceptron is still capable of producing outcomes reliably. Yeah. So the whole point was, can I have an unreliable power supply and still produce something reliable, something that I originally wanted to do? And I think we believed that we achieved that. Then we started doing a bit more work. So we started developing a real perceptron, 3x3 perceptron. So the whole idea is that instead of using the inverter, we basically use two back-to-back inverters with a little bit of smart connections between them. So something like an AND gate. So one of these inputs for the AND gate would be the zeros and ones defining weights, the different bits of a weight. And the other input will be basically the duty cycle of the inputs, right? So duty cycles defining the different inputs. So the input 1 will be a certain duty cycle, input 2 will be a certain duty cycle, input 3 will be a certain duty cycle. But we also do the transistor sizing of these ones a bit cleverly to make sure that we have a, because it is a 2's domain, so you have to multiply 2 to the power 0, 2 to the power 1, and 2 to the power 2. So you have to do the transistor sizing a bit smartly as well to make sure that the least significant bits and also the most significant bits are treated differently at the capacitor output, right? And that showed fantastic results as well. We had actually a model. We developed a very approximate model of what the output would look like if you had some sort of perceptron operation going on. As you can see, the theoretical and the simulated results or the experimental results are very close to each other, meaning that there is a high degree of robustness in the presence of power variations. And we also tried to stretch the, I think this number is probably wrong. It's in the range of 25 nanowatts you're looking at. Yeah. So can you see from the 25 nanowatt region to all the way to 400 milliwatts, the device still works. So your power supply requirements and all the manic about designing a very complicated power supply can be greatly simplified if you possibly use the analog approach of this design. Now, we've been continuing this work for a while, and one of the things we want to do is we want to design the transcoding circuit. I told you that the inputs are basically defined by duty cycles. So can we take the normal signal inputs and transcode that one into some temporal domain duty cycle information. We also started developing the online learning for perceptrons as well, and also the, because it will greatly simplify the power delivery mechanism, so can we also design the simplified power management circuit as well. And we want to implement, currently the work is in progress in implementing the complete neural network, which we want to hopefully, we are talking to ARM to get some support in fabrication and also validation of this. I'm hoping that we'll be moving positively on this. If you'd like to see, we have some more exemplars. We're working on different ends. Software end, a bit more like runtime end, not really software. System software end. How can we use, for example, OpenCL programming model or some really hardware-facing programming models to provide with transparency in energy and also management? How can we use how can we use different kinds of hardware heterogeneity in providing the stretch of the power proportionality that I just talked about? You can always follow some of the demos and exemplars that we have, and I'll be happy to take any questions if you have. Thank you.
Does anyone have any questions?
Thank you. You were showing the graph of the voltage, the power variance for different VDDs, right, on the right-hand side.
Sure.
Does that mean if you try to run your neural network or any example implementation only above 1.5 volts, you cannot go, let's say, in the sub 1 volt range, and then your model will break down? Is that a correct conclusion?
Okay, as it stands, we haven't done any significant alterations to the original inverter circuit. With a bit of alteration, we can actually stretch this one further towards, let's say, 0.7. But as it stands, you're absolutely right. You're looking at making sure that your power delivery mechanism ensures the minimum, operating point at something which is what you call as reliable.
Yes. Normally your error peaks in there. So we need to adjust the standard cell library to something
Yes. Yeah.
which works with sub-threshold.
Exactly.
Any other questions?
What kind of technology was it?
Okay, so let me just show you the circuit. Here, I did not. I basically skipped the technology stuff. So here, the width. We are using the 65 nanometer technology here, but the width was increased, doubled over here, and it was quadrupled over here. So the idea was to also compute in the 2's domain, analogously, if you like.
It's sort of digital in terms of standard cells, but we do analog things basically. And if you go to the analog end, they don't work with sub-threshold.
Okay.
So a question. One other way to mitigate those power variations would be to do asynchronous design. Have you thought and looked about that?
Asynchronous, I have the asynchronous guru right here. One of the things we had been thinking of is that when we design the, for example, the network of perceptrons, we might as well have something like a GALS. So you'll have little perceptrons who are having a clock, sharing a clock amongst themselves. But GALS is also a possibility in terms of this, if you like, that's also a genre of asynchronous computing in many ways. And then also managing the outcomes from different ends in an asynchronous manner.
In a way, the fact that we are frequency insensitive is already made in us.
Yes.
It would be easy to interface this analog continuous design with the duty cycle or PWM directly with the asynchronous logic, because we still work with 0, 1 pins. So
Right.
it's just on the way to the interface to asynchronous.
Right.
Okay, thank you very much. I'd like to say thank you to all our speakers.